Santa Clara. She received PhD from UC Masan under Professor Xueting Li. She really focused a lot of recent work on computer vision, specifically for 3D vision, affordance learning, as well as self-supervised methods. So without further ado, let's welcome Xueting to give her talk.
Yeah, thanks for the introduction and thanks for organizing the tutorial. I'm very glad to be here today to talk about deformable 3D avatar learning. So in this talk, I will briefly cover the background of deformable avatar learning methods and then introduce how we can use zero-shot and one-shot learning within this background. So 3D avatar animation has been a long-standing task in computer vision. People are interested in animating portraits, human bodies, or stylized characters designed by professional artists. This task is especially important in the sense that it has a wide range of applications, including video conference, filmmaking, gaming, or virtual try-on. So the animation methods can be roughly classified as rigging-based or template-free methods. In the conventional rigging-based pipeline, we would start with some 3D assets, usually are the meshes of human portraits, human bodies, or stylized characters in the rest pose. And then we either manually design or learn the skeleton structure, join the translations and the skinny weights of these 3D characters to enable motion. For instance, in the famous flame parametric model, the human face is decomposed into a linear combination of faces on shape or expression together with individual coefficients. So after we get the skinny models, we can then use the linear blend skinny to animate the 3D avatars for different applications. This conventional baseline is very efficient and is able to generalize to unseen identities during inference. However, it often struggles to capture the full appearance of a person or character. For example, the parametric models for human heads or human bodies only capture the facial region or the naked body, while it ignores other parts such as the hair or clothing. And also these models are usually trained on a large scale 3D scans or rigged avatars. These data are not really easily to get in real world. And furthermore, these models, they tend to struggle when the motion is rare or unseen in the training data. So sometimes it cannot capture, for example, the abundant expression of humans or in different application cases. On the other hand, recently, many works start to explore alternative representations beyond the mesh. So these models, they utilize implicit volume representation, and then they learn high fidelity, realistic, animatable avatars. So in these models, we are often provided with a video depicting the target subject. And then we can learn a deformable model with any kind of representation, such as a nerve SDF function, point cloud, or 3D Gaussians, together with a deformable field that can map the point from observed space to the canonical space. So after training, we can use the learned 3D geometry together with the deformable fields to animate the character during inference. Those methods, they often produce very impressive high quality results because the powerful implicit representations that they use, but they struggle to generalize to arbitrary subjects during testing. For example, in one scenario, if we want to create a 3D head avatar for video conference, we will have to capture a multi-view video of the specific person first. But how good the model can learn largely depends on how good the captured video is. So if the video can cover all views of the portrait, then we can expect a good model. So in another word, these models, they usually overfit to specific subjects, so they cannot easily generalize to arbitrary objects, and meanwhile, they cannot utilize the prior from the whole category. So now let's consider some more challenging but practical applications where we don't have videos or paired motion data for training or testing. For example, what if we only have access to a single view portrait photo instead of a multi-view video of a person, but we still want to animate the person in the photo? Or in a fancier application, we are just interested in animating unrigged animal meshes, but it will be really hard to find a larger scale dataset of rigged animal meshes for training. So in both cases, existing avatar learning methods would fail because of their strict requirement for training data. So in these cases, the one-shot and zero-shot learning would largely ease the requirement on training data and also enable the model to generalize to arbitrary subjects during inference. So next, I will use these two applications as examples to see how we can use one-shot and zero-shot learning when data is limited. The first application I will talk about is a one-shot avatar animation, where a model takes a single view portrait image as input and render it at arbitrary head pose and expression. The second application, we aim to animate unrigged stylized character, and in this case, we don't even have paired motion data for training. So we solve the problem in a zero-shot manner. I will start with the one-shot head avatar animation work. So there already exists a large amount of portrait animation methods, starting with the classic parametric models. These parametric models are learned with a large-scale scanned 3D data and can be generalized to unseen identities. But they are mesh-based, so their texture resolution is limited, and they cannot capture regions beyond the face area well, like the hair, accessories, or if the subject is wearing a hat. At the same time, there are also 2D GAN-based talking head synthesis method. So this method, they can synthesize photorealistic images when the input and the rendering view is both are both front or near front view. But because they don't capture the underlying 3D representation, these models sometimes suffer from warping artifacts and identity shift when we render the avatar from extreme profile views. Well, recently, there are also lots of nerve-based avatar animation models. So these models, they have really impressive results. They even capture the background very well. But these models, they cost hours to learn a single model for each individual, and they also require multi-view images or videos for the training process. So in this work, we target at a more practical application case. Our input during inference is only a single view portrait image, and we aim to reconstruct its 3D shape and animate its motion according to a given target video. And more importantly, we want our method to generalize to unseen portrait images without requiring adding test time optimization. And meanwhile, we want to capture the photorealistic details within and beyond the face region. So to resolve these challenges, the key idea we have is to disentangle a model. It is to disentangle the geometry, appearance, and motion in a unified model. And then we learn the model with a large number of single view images, videos, and also synthesize the data from 3D GANs. So that during inference, it only requires single view image as input. And here is the overview of the framework. It includes 3 branches to model the geometry, texture, and expression respectively. So I will introduce each branch in detail. We start with the canonical branch. This branch takes the source image as input and reconstructs a trapline capturing the close geometry and texture of the portrait. We adopted the trapline representation because it's very memory efficient. It's also very easy to be integrated with 2D convolutional neural network. And also it shows strong performance in previous generative models. And in this branch, we also have an extra constraint that enforces the trapline to produce a neutral expression. By doing so, we are wiping out the source expression in this branch. So this will make the expression branch learning later on easier. Here we show the rendered image of the canonical trapline. So we can see that the rendering has neutral expression, but it lacks photorealistic details in the input image. This is because single view 3D reconstruction from 2D images is essentially a holistic process. And if we only use a single encoder, the encoder will focus on reconstructing the cross geometry, but ignore the intricate details in the input image. So to capture the details in the input image, we propose an appearance branch. In this branch, we first map the source portrait image to 2D feature maps. And then we can use the depth map rendered from the canonical trapline to build a neural point cloud. So each point in the neural point cloud corresponds to a pixel in the source image. We also attach the corresponding feature vector from the 2D feature map to each point in the point cloud. The intuition behind this design is that if we directly lift the 2D image into 3D using the camera pose and the render depth, then we hope to maximally preserve the texture details in the final reconstruction. But one problem is that the point cloud is essentially not inherently compatible with the canonical trapline we got from the canonical branch. So we rasterize the neural point cloud to create appearance trapline. By adding the appearance trapline to the canonical trapline, we can capture realistic details in the portrait image. So here we visualize the render image of the combined trapline, and we can see that this rendered image can reconstruct some facial details, such as the mole of the person on the left face. So the canonical branch and the appearance branch essentially capture the identity of the source person. And we also target to model the expression. So we propose a third branch, which is called the expression branch. In this branch, we use an off-the-shelf 3D multiple model to render a frontal view image. This image has the identity from the source image and the expression from the target image. Then the expression encoder takes this frontal view rendering as input and outputs an expression trapline. And by adding the 3 traplines, the canonical, appearance, and expression traplines together, we have our final animation 3D animation results. Then we can carry out the volumetric rendering on the final trapline to produce a low resolution image with both desired identity and expression. And finally, we also have a super resolution block to synthesize the high resolution animation results. Yeah, so this is the overall view of our framework that disentangles different components. And during inference, if we want to carry out the expression transfer, we can simply feed the driving images through the expression branch to produce the expression trapline, and then combine the trapline with the identity trapline. to animate the person in the source image. And we train the whole pipeline with reconstruction loss by comparing the animation results with the target image. And we also have the GAN loss for to encourage photorealistic rendering. Also a smoothness loss on the trapline to encourage a smooth surface, and also the neutral constraint to encourage the canonical branch to have neutral expression. And for the training data, we use as many data as we can find. That includes single view images, talking head videos, and also synthesize the training pairs from previous 3D aware GAN model. So all the training data are in the 2D scenario, so we don't have any access to any 3D data. Here we also visualize the contribution of each branch to better understand the model. So we can see here, if we only render the canonical trapline, we can have a coarse reconstruction with neutral expression. And by adding the expression trapline on top of the canonical trapline, we can modify the expression to match the one in the target image. And finally, if we further add the appearance trapline, we can capture the details, such as the cross pattern on the nurse's head. Okay, so now I will show some results and a comparison to baselines. So here we compare to a mesh-based baseline called ROM. And thanks to our trapline representation, our model can capture better details in the input image. And we also compare to 2D talking head synthesis method. So this is one state-of-the-art method called style heap. So because our model explicitly reconstructs the underlying 3D shape, it's more robust to pose change as well as identity shift. And finally, we also show more animation results on different identities by our approach. So we can see the motion from the target video can be transferred to each single view image. One limitation we observed in our model is the inferior deformation for some rare expressions, such as the wide jaw opening. We found that if we use some better synthesized data, for example, if we replace the data from a static GAN model to a dynamic GAN model, then we can this limitation can be largely addressed. But we still think the current design of the deformation branch is limited because we are essentially capturing the expression in the expression trapline. This does not really match the physical world, which our expression should be represented by a real deformation. And we think the deformable nerve is always an independent and challenging research topic, and it could be a very interesting future work. And here are also some concurrent one-shot 3D avatar works. So all these methods during inference takes single view images input and then produce 3D animations of the avatar. So if you are interested in this topic, you can also check out these works. So this concludes our one-shot portrait animation work, where we learn a multi-branch model with a larger scale of mixed dataset. And after training, after encode the dataset prior into our model, we can use it to carry out one-shot avatar reconstruction and animation. In this case, we still have some motion data about the human portrait. Although they are not 3D, they provide a lot of information for how the expression changes. But what if we don't have any motion data on the target avatar at all? For example, what if we want to animate unrigged stylized characters shown on the left? So next, I will move to our work on zero-shot post-transfer for unrigged stylized 3D characters. In this work, our input is a source human pose and a target stylized character in the rest pose. And our goal is to transfer the pose from the source human to the target character. And most importantly, in our design, the target stylized character is just a T-pose mesh without any rigging information. So there are a lot of these stylized characters on the internet. This setting makes our work very practical, but meanwhile, it's also very challenging in the sense that we don't have any care data for training. So this setting differentiates our method with existing approaches for post-transfer between characters. These existing works, they either require manual rigging annotation or paired data in rest and the target pose for both the source and the target characters for training. On the contrary, our model only requires easily accessible post-human meshes for training. And theoretically, we can synthesize an unlimited number of post-humans using the SMPL parametric model for training. So this setting makes the model very challenging, but it also makes it very practical. And during inference, the model can be directly applied to animate an unseen stylized character during this drive mesh sequence, or giving a drive video clip. So to achieve this zero-shot setting, we depend on two modulars. The first one is the shape understanding modular that maps a 3D character to a shape code. And the other is a post-deformation modular that repos the character conditioning on the shape code and also a given post code. And furthermore, to guarantee high transfer quality, we also introduce a test time training process with some regularizations to encourage smooth transfer results. And I will introduce each modular. So the shape understanding modular encodes the shape information of a given character into a shape code. It takes the shape code, a querying point as input, and then learn a network to map their concatenation to an embedding. From the embedding, we can predict the occupancy and part segmentation of the query point. Because we use the SMPL to synthesize our training data, we have the ground truth, occupancy, and the part segmentation label for supervision. But to further generalize the shape understanding modular to stylize the characters, we also include dozens of unrigged characters in the rest pose for training. Because these characters, they are unrigged, so we don't have ground truth part segmentation labels. And to further constrain the learning on these unrigged characters, we propose an inverse constraint. So we train a network that takes the shape code and the embedding as input, and then reconstruct the position of the query point. So this way, we encourage the model to differentiate different points with the same occupancy and part segmentation label. After we get the shape code, we are ready to transfer the pose. So we develop this pose deformation modular that takes the shape code of the character, a target pose code, and also query point as input, and then it outputs the it then uses a multilayer perceptron to predict the offset of the query point. And by deforming all surface points with respect to their offsets, we can deform the input character to the desired target pose. And one detail here is that where do we get the postcode? So we actually sample the postcode from the latent space of a pre-trained model called vPoser. And this brings two benefits. One is that it can utilize the post per hour learned from a large scale dataset The other is that during inference, the postcode can be extracted from different modalities by existing words. And this will make our model easy to transfer poses from meshes, images, or videos onto stylized characters. And although the post deformation modular often have reasonable results, but we found sometimes it struggles to preserve the volume of each part. For example, sometimes we would observe that the arm of the character is crushed during the transformation. So we further fine-tune the post-deformation modular with volume preserving constraint. And this is the formulation. Intuitively, we randomly sample point pairs within each part on the surface of the stylized character. So the part label is predicted by our shape understanding modular. So after we sample these point pairs, we enforce their Euclidean distance to be preserved before and after the post transfer. So here we show two sampled point pairs in blue and red, for example, and we observe in this way the shape of each part or the volume of each part can be roughly preserved, and this leads to more natural and realistic transfer results. So now I will present the results of our method. Here we first visualize the part segmentation prediction by our shape understanding modular on the stylized characters. So although we don't have ground truth part segmentation label for these characters, we only have ground truth for the human meshes, but we can see that the model can generalize well to these stylized characters and present reasonable part segmentations. And we also show some comparisons for post-transfer and on two baselines. So here one baseline is the NBS baseline trained on naked and closed humans, but we can see the struggles to generalize stylized character, which has different topology. For example, here the hair in the baseline is detached from the body, but our model can preserve the hair well. And we also show this challenging case where the stylized character has a really big head. So this is really different from the training data, but the model can still produce reasonable animation results. And we show some example on transferring poses from videos to stylized characters. So in these cases, we use off-the-shelf pose estimation method to extract the pose from the video, and then use the pose code to guide the stylized character. And finally, to show the true generalization ability of our method, we also train our model on quadrupeds synthesized by this SMAL model. So this is a parametric model for quadrupeds. And after training, we apply our model to stylize the animal character. And in this case, the zero shot is really important because for animals, it's even more hard than to collect rigged meshes than human-like characters. So this concludes our zero-shot avatar learning work, where we learn a post-transfer model with post-human data and apply to unseen stylized character in a zero manner during inference. That's all I would like to include today, and I'm happy to take any questions.
Thank you, Xueting. Thank you. Yeah, any questions from the audience? All right, I do have one small question on the facial zero